What else before we proceed? Ayun, no, yung student survey, I posted a survey last, when was that? Last Monday, no? I was asking for some questions, maybe perhaps to guide us um, further, no, on what materials or specific topics that we need to enhance in this course. So far I've seen 70 responses. So you guys are I'll encourage to check our stream page, and the survey was posted last Monday, no? Yeah, so kindly check the survey questions, and just fill out the forms, no, for your responses. Okay, so this begins our introductory concepts, no, for electronic circuits. We will cover various electronic devices, no, in this course. So what's in it for you, no, as future mechanical engineers? So initially, in for those who have already responded in the survey, no, though we're gonna have to treat I'm gonna treat this with ano naman, no, parang confidentiality or sensitivity. But just to share some insights, no. Some of you would wish to pursue careers in the manufacturing sector and automation. So I've seen stuff like that. Okay, so I suppose I've done some introduction myself last time. So again, I'm Engineer Silverino Magon. I am an ECE by training, and I'm an automation professional, no? By automation engineer or instrumentation and control by profession. So in my line of work, I've had years of experience and exposure to the manufacturing sector, and on a regular basis, as automation professionals, we interface across diverse fields of expertise, no? Like chemical engineers, uh, mechanical engineers like you guys, electrical engineers who are dealing with the power systems. And again, as for my part, automation people like me, we deal with the various systems or subsystems related to control and automation. So mainly, we handle circuits with small signals, which are used for communication, and that when if we want to automate plant manufacturing, you know, so there are various peripherals, you know, like motors, valves. You know, those are your what we call the actuators, moving parts essentially. You know, they are in many cases they are supplied by different power levels. Induction motors, for example, are supplied by low voltage to possibly medium voltage AC sources, but the command itself to start the motor and the monitoring of the status of the motors are done using small signals, no? Automation. So small signals controlling larger signals, enabling the continuous operations of motors, valves, and in effect the plant itself. All right. So anything else? Again, now for those who haven't um, responded yet to the survey, kindly accomplish the survey questionnaire. I posted the link in the stream page of our classroom. No? All right. HVACs are some of the aspects na we deal with. ACUs, energy monitoring and consumption, though those are also part, no, or parameters or dimensions of uh, process process engineering that is being monitored or evaluated using critical instruments as well. And automotives definitely, no. So automotive engineering nowadays is no longer purely mechanical, no? If you've been aware of more recent advances in car manufacturing, uh, all the all the processes involved in running a car is done almost automatically, no? Or with the use of electronic controls. Yun. So anything else? So I'm just checking some of the responses. Do you guys have your ICE subject already? Meaning internal combustion engines. Can you say show of hands? I just like to check to check if you guys have completed your in what subject will that be? No? Internal combustion engines. ICE. Ah, yes.
Bali na-take ko na po sir, bali ang tawag po sa amin ay combustion engineering, pero na-discuss din po yung internal combustion engineering.
Okay. Okay. So yeah, thank you, thank you. So you're that's one of the important major subjects, in your field. So internal combustion engine. So as no, sa uh, gasoline engines, no, spark plugs are run using electrical or electronic supplies. But the nowadays, yung optimization ng air fuel mixture, which is something you study uh, intensively, no, in your field. These are all being controlled automatically, no? Numerical controls using computers. No? So sa colloquial term, we refer to the computer box. No? So almost all cars being marketed today have or contains electronic controls to essentially well control, monitor the status of your engines, and then later optimize the operation. Yun. So ang labanan ngayon with in terms of the the market competition nowadays, no, in car manufacturing is optimization in yung cleaner engine or more efficient uh, engine performance. No? So that is being done with the help of electronic controls. And I suppose more modern cars. have around thousands or hundreds lang naman, hundreds to almost a thousand of sensors. Uh, I was mistaken pala, no? So I was referring to an F1 car, no? But if you were a follower of Formula One, no, modern F1 cars, they have around almost a thousand. So all the critical functionalities of high performance cars are being monitored using electronic sensors. No? So they are able to uh, pinpoint the location of the cars in the track, stuff like that. Yung steering itself are being monitored. Of course, yung RPM, stuff like that. Those are the usual stuff. Na even the commercial cars, we do have that, no? But for F1, there are so many parameters that are constantly being monitored so as to ensure the maximum operating condition. So later we will see how some of these devices operate, and hopefully it will start to make sense now once we understand how modern electronic devices operate. We can get to get a glimpse of how we can have practical applications for these devices. Okay, so yeah, so maybe we can start with some of the key insights. Okay, so yeah, this is something I think. Let me check if I can change this now. So anyway, as you know, this is a service course from the EC department. 421 or 4 and 422 are essentially the same. It's just that the 421 course is the same equivalent course as this one being offered to CPE, or computer engineering students. But essentially, the course content is pretty much the same as what we have here. So we begin by our analysis or review of some chemical properties, no, that where the semiconductor physics originated. No? Okay, so yeah, so we will have a review of how an atom is structured. No? So from this topics, no, we will define how insulators, conductors, and semiconductors are chemically different from each other. And then with these underlying principles, a semiconductor is formed. No? We will go through the properties of semiconductors or compound semiconductors, which are sort of chemically synthesized, no, to form uh, the derivatives of the N-type and P-type materials. And then something happens when we combine these materials together. Right. So and system nowadays are getting incredibly smaller. No? Current speeds of operation vary significant, and new gadgets are released every day. And in almost all areas of technology, fundamental principles uh, change very little. No? Yung chemistry aspect, yung physics aspect, uh, I think has been around in early 1800s to 1900s. Uh, it remains the same, no? So we will go through the introductory chemistry topics once again, just to uh, form a basis. No? So the first device that will be introduced here is the simplest of all electronic devices, but it has a really wide, numerous array of applications. Okay, so how many of you have heard these terms? Now, diodes, can you see a show of hands? If you've heard of these terms before, show of hands or reacts, anything? Don't worry, guys. No, I will not ask you how these things operate. Okay, so maybe you've heard of this in your earlier courses. No? So maybe 419. Yeah, is that right? Okay, so diodes. No, so we have the diodes. How about transistors? Show of hands or any reacts? If you are familiar with the concepts of transistors. All right, thank you. So back in the days, no, we are around 50s, 60s. Hindi na natin inabot, no? When people talk about transistors, they are referring to the small handheld radio, no? Transistor radio. But that is essentially uh, an AM receiver that operates on with the use of transistors. So it's a transistorized radio receiver, no? Because transistors are relatively small electronic devices. The footprints or the form factors are very small compared to its predecessors. That's why it enabled the more portable versions of our radio receivers, and of course ICs. Yeah, that's why these uh, uh, remote mode, no, of session is made possible because of the portable electronic devices that we have, which are mainly made possible by ICs. And these are all formed out of semiconductor materials. Now, an important concept presented in this module is the PN semiconductor. Okay, so yeah, yeah, yeah. So this is a form when two different types of materials are joined together, and it also plays an important role in the operation of these devices and similar devices like solar diodes, of course, solar cells, no, rather, and the diodes and transistors operate on this basis. So this module will present the construction, characteristics, and models of the semiconductor diodes. All right. Um, Back to basics. Now we again have to define electronics, and there are actually sort of a legal definition for this. So the first Radio Control Act defines electronics as the science that deals with the development and application of devices and systems involving the flow of electrons in a vacuum, no? Or gaseous media or plasma, and of course, more recently, semiconductors. Now, the electronics engineering law defines electronics as the science dealing with the development and application of devices and systems involving the flow of electrons or other carriers of electric charges, charge in the vacuum, in gaseous media, in plasma, and semiconductors, in solid state, and or in similar devices, including but not limited to applications involving optical, electromagnetic, and other energy forms when transduced or converted into electrical signals. So we have the legal definitions for this. So there are various bits of practice that is which are regulated by some legal frameworks. No? Okay, so can you kindly examine first the image, no, on how this structure here is described by the symbol on the left hand side, no? And we'll go through the description and the history of this device. Okay, so we have here the two electrode vacuum tube. No? So, ano lang, quick poll guys. Who among you plays the guitar or uh, yeah, particularly electric guitars? Are you guys familiar with the electric guitars or how electric guitars work? Anyone? Show of hands, maybe. None so far. Okay, so how about rock music? Sinong nakikinig sa rock music? Anyone? Wala din. Only one? Sige. Sige. Yeah, thank you guys. So some fans of rock music here, but none of you plays the guitar or any sort of familiarity. Okay, so I mentioned this because the device that we have here is an electron tube, no, or a vacuum tube. uh, Earlier versions of amplifiers are built out of these things. No? So let's go through first the history. So the first vacuum tube was introduced by Edison and John Fleming in '04. Now Edison, they recognize uh, inventor or who made the incandescent bulb uh, popular, had also introduced that the direct electric current flowed from a heated metal filament in the bulb to the other electrode only when the latter had a positive voltage. No? So John Ambrose Fleming used this effect, otherwise known as the Edison effect, to invent the two electrode vacuum tube rectifier. And this soon become an important discovery, and then the applications of which have been implemented across different electrical applications. Okay, so the concept here is that um, electric current flowed from heated metal to the other electrode only when the latter had positive voltage. No? So as we know in basic chemistry, the similar charges attract, and the opposite charges attract, and similar charges repel each other. So this is the same concept. Nothing new here. No? It's just as that this concept is used uh, more specifically to control na, rather than just attract or repel. No? So it's not only on off, but to control the flow of electric current. Yes, that concept of uh, attraction and repulsion uh, were used, and that is in the case of switching applications. No, you apply positive charge, and the current will flow. You interrupt that positive charge or positive voltage, and the current stops. Or even further, you can sort of reverse the voltage, and similarly, the current will cease to flow in and across the uh, filament. No? Okay, so does that make sense? Any confusion? So babalik pa rin tayo sa principle na opposite charges uh, attract, and then same charges repel each other. So that's the basic operating principle of the vacuum tube. And later some adjustments were done. No, that the positive voltage shear through some series of experimentation. It was discovered that increasing the positive voltage will what further increase then the electrical current flow. So essentially, you can control the current, no, from the actually from the anode to the cathode, no, by controlling the uh, positive voltage in your grid. Yeah, so that's how the basic amplifying action operates. So you can just apply positive voltage and remove the negative voltage, so that becomes an on-off condition. Or you can apply positive voltage and vary the intensity, no, the levels of that voltage. So what happens is that the current flowing across the filament will vary as well. No? So the current flowing through the filament will vary as well. Okay, so that's the basic principle of amplification. Kasi what we're having in the grid, no, as your controlling element, is that this positive voltage here is of a relatively small value. No? Kasi millivolts, milli is in the thousands pa, no? So in the thousands of volts. You're controlling a fraction in terms of a fraction by 1,000, no, millivolts, controlling something in the filament in terms of volts. So that's 1,000 to 1. So a small voltage controlling a bigger value. So that's the amplification action. Okay, so um, are you guys familiar with this device right here? Inabot niyo pa kaya itong vacuum tube na CRTs, no? Sinong nakakita ng CRTs? Cathode ray tubes or tube television sets. Show of hands or reacts if you have seen a CRT before, cathode ray tube television. Anyone? Reacts or uh, so some have seen it, and but many haven't seen it yet, no? So that's how fast things are evolving. Actually, actually, my generation inabot pa namin, no? We were the generation who experienced this transition from uh, analog to digital, no? Actually, last week lang I attended a talk from a senior engineer from uh, GMA, no? Na he shared some stories on the digitization of the Philippines. Uh, na we sort of adopted the Japanese standard ISDB terrestrial, and the are underlying events that led to that adoption. Of course, well, maybe most of you don't know this, but uh, TV standards, no, are different across nations or different countries. Most of these standards were developed by superpowers like US. No, they have different standards compared to the EU countries. Now, in our case, we opted for Japan standards, but that is mainly because of some key events that resulted to the National Telecommunications Commission adopt Japanese. To put it more simply, because the equipment, shall we say, the equipment were more accessible for us. No, the equipment from Japan were more. I guess the a fair and simplest way to describe what happened. Um, but before the digital TV, even yung mga flat screen TV na inabot nyo, they were operated initially, no, using analog signals. During the transition, no? We have the TV box, this to improve the signal quality from the analog signal, so that it can be implemented properly dun sa mga flat screen TVs natin. But back then, back then, uh, we don't have flat screen TVs. No? Flat screen of semiconductor. The screen itself is an array of light emitting diodes. So depende sa technology. We have LCD TV, we have LED TVs. No? Liquid crystal display and light emitting diodes. Those are two different sets of materials. Later we will go through the LED operating principle. It made it possible, no, for TV sets to be formed in the form factor that we see today. Now, the footprint is relatively small, super thin form factor, But some years ago, that was not possible because the earlier televisions were made out of tubes. No? So here is a an example of a TV. The screen itself is a huge vacuum tube. The operation is rather more complex. No? If I try to explain it today, it will take up so much of our time. But just to give you an idea, uh, this is a huge tube. No, we have the smaller tubes like something that we've explained earlier, no, in the previous slide. In actual physical manifestation, looks like this tubes right here. So this is one tube. This is another tube, and these are some other tubes. You can see the appearance. Na there are these three, I suppose, are similar models, but these other guys here, these guys are the different models. So there are reasons for those things as well. The different models have different current or voltage ratings and amplification capabilities. No? So that's why some tubes are bigger than the others. Okay, so yeah, so the first commercial TV broadcast began around 46. Uh, hindi naman tayo nahuli back then, no? I suppose the predecessor of ABS-CBN. They have the Alta Broadcasting. Some American guy, no? If you read or if you read the history of ABS-CBN, some American guy who immigrated in the Philippines married a Sinense. No? So that's why the earlier broadcasting uh, firm was called the Bolinao Broadcasting Corporation. So something like that. And we were not that left behind, no, because that time the American presence was still very felt, no, across the country. The first vacuum tube was built in 43 by UPenn. It was a computer but with very limited capabilities. I think you've done your NUMETs, no? NUMETs, numerical methods. Show of hands. If you can still recall your NUMETs. Anyone? Yun. So in NUMETs, you've learned of some things or calculating, no? Calculating or performing complex calculations using different iterative methods, addition, subtraction. So that's how modern computers are able to perform complex calculations. No? Calculus being done by computers na initially is basically capable only of addition and subtraction. But back then, the earlier computers were very limited, and much respect, no, for the earlier engineers who developed these systems. Because although the capabilities back then were very limited to simple additions, so things like that, they persisted, and they had the foresight, no, to think that future computers will evolve out of these principles to be capable of more complex calculations. But basically the history of computers show us that the earlier prototypes were of very limited capabilities. So the simple addition, ganon, simple adder are done by uh, earlier devices like this. So very bulky, no? Very bulky because each tube. or each amplifier set can only perform one calculation, no, parang 1 plus 1, something like that. And if you want to perform extensively or computation across big numbers or using big numbers, and then so you need the thousands of devices like this one. So earlier computers were really massive. Um, if you've heard of the history, like the Mark One, MIT has their own early versions of computers. Uh, ENIAC, and those are the earlier computers. Uh, the electronics alone occupy so much space, no, in form factor na parang it requires a huge house or parang warehouse like something to store and safe keep the computers. The same capability is can be done by a very small integrated circuit. No? More to compare with the more modern computers, the same capability can be done by a very small integrated circuit that can fit the palm of your hand. Actually, yun, sa thumb mo kasha na din siya. And even more, no? It can perform even more complex and more advanced calculations. Now, the revolution happened during um this period, no? 47. Actually, it was in the eve of on the eve of Christmas Day, where or when um, Brattain and Bardeen of the Bell Labs introduced the first solid state transistor. Okay? Solid state in the sense that if you allow me to go back to the previous slides, no? Yan. We have the vacuum tube, no? So this is a tube, a glass tube, which is filled with gas or inert gas. It's not, in many cases, it's not really vacuum. We just refer to it as a vacuum, but it can be filled with an inert material. Inert is a term in chemistry that means that with the given conditions, the chemical, the gas, or the substance inside will not react. It will remain chemically neutral. No? So it's an inert gas. So there are cases where an actual vacuum is used, but as you know, in your prior maybe chemistry or physics class, that a perfect vacuum is actually very hard to achieve. No, so instead of an actual vacuum, an inert gas will be a really good substitute. Okay, so let's go back to the semiconductors. So the vacuum tubes were either vacuums or gas filled tubes. No, now with the advent of the semiconductor transistor, hindi na kailangan, no, ng gases or all that bulky stuff. And these devices are made out of very compact, very small semiconductor chips, no, or bits. That's why these devices are referred to as the solid state devices. You don't need any gas to build switching devices and circuits out of these materials. So this is something in the It can be found in the um, Museum of Bell Labs, no? And this is the replica na lang. So, not quite sure, no, if the original point contact transistor was still preserved or its whereabouts. You a quick search online, no, you can see the some earlier image, no, of the first actual device. So they recreated the stuff and then present the replica in their museum. The device itself was actually co-developed by these two guys, Bratin Bardeen and Dr. William Shockley. No? So these are all researchers from Bell Labs. Only it's just that the Bratin and Bardeen were there during the presentation. Not sure where the on the whereabouts of Dr. Shockley when the time. But Shockley was actually the theorist, no, the formulator of the idea of the uh, bipolar junction effect, which created the transistor. So later, maybe next week or 2 weeks from now, we're gonna cover the discussion on the transistors and the amplifying actions. Okay, so transistors can come in all forms. First is that if you look at the right image, that's the schematic symbol. If you see anything like this one with the arrow, yan, transistor yan. There's no any other device that that looks like this one. So this is a BJT or bipolar junction transistor in particular. Basically, it can be in this package, no? And then the TO92 or transistor outline, the very popular package like this one. But the actual transistor itself is inside those packaging. It's very small, no? Parang uh, how small is the strand of your hair? No, if you look at the cross section of your hair, it can be even smaller than that. So small that it may not make sense to put a picture on it on display or in this presentation. No, I can only show you the packaging, but the actual device inside is very small na hindi nyo makikita siya. It's really very small. That's why it made more modern computers possible, no? That we can fit in hundreds, not only hundreds but thousands, and more recently millions, no? Millions of that transistor devices in one very small chip package. Your CPUs that you have in your computers, so that there are millions of these things inside your computers. That's very small. Now, I cannot show you an image of an actual transistor. If you want to look at the semiconductor stuff itself, you cannot see it. You can only see the packaging outside. So it's very small. We will go through the specifics in some later sessions for us to gain better appreciation of how these things works. But the principle, similar to the vacuum tube, is essentially the same. No, you have a small current, or voltage. Either way, no, it's possible. A small current or small voltage, controlling bigger current or bigger voltages. So that's the amplification. Um, Thanks to these three guys, all the more modern um, developments in the field of electronics were made possible, no, because of the invention of their invention of the transistors. Um, These three guys received the Nobel Prize in Physics for their contribution. Uh, but the good guy here, Dr. Bardeen, were one of the few. I think there were only two guys in history who received the Nobel Prize twice, and Dr. Bardeen is one of these. Uh, Besides the transistor as his contribution, he made other contribution in the field of um, condensed matter physics, I think. No? So if you look his profile, a certain phenomenon in physics called the BCS effect or BCS theory was named after the discover after the people discovered that event. So that's called the Bardeen Cooper Schrieffer effect. And the Bardeen in the BCS, the B in the BCS, is Dr. John Bardeen. Okay, so further advancement, no? I mentioned of the IC already. No? The CPUs, that's some of the ICs that you're familiar with. No? So early ICs were the earliest ICs, no, were built by Jack St. Clair Kilby of Texas Instrument. There was another claims of the other co-inventor, so I'm just figuring or trying to recall the name. No? But Jack Kilby was one of the pioneers of the IC developments, no, integrated circuits. And it further accelerated, no, this development further accelerated the miniaturization trend in semiconductors. So ICs are a complex combination of several kinds of devices on a common base called the substrate or any piece of silicon. So the earlier IC that was developed by Jack Kilby, I think it contained only 12 lang yata, no? Parang 12 transistors. But more modern ICs, the deep dual inline package that you see here in this row here, and then the solder mount device, SMDs, you can see here. This can be microprocessors, of course, CPUs, microcontrollers, and yeah, more modern CPUs, no? Like the ones you can see in your laptops, Intel, AMDs. Those stuff contains thousands or up to millions of transistors. So further developments happened, but it all started with uh, Jack Hilby. No? In terms of applications, there are numerous. Actually, there are more further applications beyond what are listed here. No, of course, communications, AM and FM radio. Quick poll, guys. Nakikinig pa ba kayo sa AM or FM? Do you still listen to AM or FM radios? Show of hands, guys. If you are still listening to AM and FM. Wala na. AM and FM, guys. Quick poll lang. Or any reacts, no, if you are still listening to AM or FM radio. Sad to see, no, na there are very few followers. Siguro yung mga parents nyo, no. You guys are fortunate, no, because of the massive digitalization, no, that nowadays almost all the areas of uh, whether in Batangas or some of you are in Laguna, are all already covered by GSM or cellular networks. So that's why you can access and join your classes anywhere. Some of you may be complaining about the crappy connection or quality connection, but still you're connected, no? So that's something that you need to appreciate. Yes, there's so much to be desired in the quality of communications in the Philippines, but at least we have almost all the areas covered already by cellular communications. Back in the days, siguro I think mga 10 years, 15, or siguro safe to say 20 years ago, there are still areas back then na hindi covered ng GSM or any form of mobile communications. No? So not that long ago, people are still using AM and FM radio for their source of news and entertainment. Nowadays, anyone can connect through their mobile devices and browse through social media, and they have their daily dose of news and entertainment. No? But still, we still have the AM and FM services available if you if you have an AM receiver, FM receiver, tune into some stations. Maybe when you're traveling, no? If you're commuting, or if you have a car, then maybe you can turn on your radio. If you don't have your Spotify ready, or if you're losing data connection, you have the option to switch on your FM radio. You can still hear uh, something. No? It's still the AM and FM are still ongoing in terms of its broadcast. Okay, so electronics also play an important role in the control of monitoring of electrical systems in power plants, refineries, and as I mentioned, manufacturing facilities. No? If you have really large manufacturing plants, yeah, so that's some of the applications where electronic monitoring and control is very important. Yung mga substations, no, like what we can see in Meralco, they have their SCADA as well, supervisory control and data acquisition. So all of these makes you make use of electronics and computers. Digital electronics, it's almost self-explanatory. You have your calculators, computers, data processing and communication. Automotive, I mentioned that this stuff earlier. Uh, yung timing ng ignition is something that's being regulated by computer boxes. Yeah, and then anything else? Back then, no, nung wala pa yung ganyang technology, ignition was parang mechanically controlled. So it's something that is synchronized, parang using either the crankshaft or the camshaft to create some electrical contacts to supply the spark plugs, and then that's how things work. No? To synchronize the spark plug or stroke, no? For you guys who are, of course, you guys are more familiar with the operation of the combustion engines. Industrial electronics, of course, yung heating, HVACs, no? I've seen some of you guys mention of HVACs as a particular field of importance. Of course, the controllers, no, for heating, ventilation, and air conditioning are done electronically. Elevators, welding processes, cupping machines, no? Automatic door openers, and um, built-in monitoring systems, no, like your burglar alarms. No? So those are of course done electronically. Medical devices, of course, are developed using electronic devices. Yun, so let's go through the review. No, so the we go back to the humble or simple atom. No, and we can recall from our chemistry classes that the atom is the smallest particle of an element that possesses the unique characteristics of that said element. No? All matter is composed of atoms. All atoms consist of electrons, protons, and neutrons except normal hydrogen, which does not have a neutron. Normal hydrogen. So meaning to say there is a hydrogen which is not normal. Are you guys aware of that? Show of hands or any reacts. If you guys are aware of the hydrogen which contains a neutron, just to check no if you can still recall chemistry concepts. It says here na a normal hydrogen daw does not have a neutron, no? In our later discussion of electronics, wala naman tong uh, purpose for us, but just to check if you can still recall your chemistry. So normal hydrogen does not have a neutron, meaning to say there is a hydrogen that does contain a neutron. Are you guys aware of that? Show of hands if you are aware, or any reacts if you're not. No, so some people are aware, some are not. Okay. So there is actually hydrogen that does have a neutron. It's called the heavy hydrogen or the deuterium. So just a trivial stuff. Maybe you'll encounter some of these things again when you review for your board exams, maybe. No? So each element in the periodic table has a unique atomic structure, and all atoms for a given element have the same number of protons. No? So Neil Bohr proposed that the electrons in an atomic circle, the nucleus in different orbits, similar to the way planets orbit no, or revolve around the sun in a solar system. So the Bohr model is actually referred to as the planetary model. No? Yeah. So just to form, parang refresh you guys know of the concepts of these things. All right. Yun, no? So that's the Bohr model. So according to the classical Bohr model, atoms have planetary type of structure that consists of central nucleus surrounded by orbiting electrons. Now the nucleus consists of positively charged particles called protons and uncharged particles called neutrons. Now the basic particles of negative charge are called electrons, and each type of atom has a certain number of electrons and protons that distinguishes it from the atoms of all other elements. No? So that's the parang determining factor or identity ng element, no? The number of electrons. So the atomic number equals the number of protons in the nucleus, which is the same as the number of electrons in an electrically balanced or a neutral atom. Energy levels, right? So the electrons orbit the nucleus of an atom at certain distances from the nucleus. Electrons near the nucleus have less energy than those in more distant orbitals. So the further away you are from the nucleus, so you have uh, more energy than those. So again, no, the near the nucleus you have less energy. Uh, further or farther electrons have more energy. So each discrete distance from the nucleus corresponds to a certain energy level. In an atom, the orbits are grouped into energy levels known as shells. A given atom has fixed numbers of shells, and each shell has a fixed maximum number of electrons. Now, the maximum number of electrons in each shell is this, no? So, number of electrons is twice the n squared, no? So, the n is the the shell. All right. So, this is just a recap, no, of what uh, all of you guys have covered in your earlier chemistry. Okay, valence electrons are yan. So the electrons that are in orbits farther from the nucleus have higher energy and are less tightly bound to the atom than those closer to the nucleus. This is because the force of attraction between the positively charged nucleus and the negatively charged electron decreases with increasing distance from the nucleus. Yan. So the outermost shell is known as the valence shell, and the electrons in that outermost shell is called the valence electrons. Yeah. So the thing is that concept of the valence electrons define or describe the electrical properties of the material. Okay, the free electrons are electrons dislodged from the outer shell of the atom. This is by virtue of the external energy sources, like heat itself. No, okay, so what are the sources of heat? Environment. No, what if we are in a room temperature? Will there be a source of heat? Any guess or any insights? What do you think, guys? What are our sources of heat, no, if we are working or operating in a room temperature? What are the sources of heat? Sa room temperature, any ideas? Okay, so the room temperature itself, no, provides the heat level necessary for the valence electrons to be dislodged from the outermost shell. The mere fact na you are not operating at 0K, no? You guys know what 0K is, or absolute zero? What is it in centigrade? So just to refresh our memories, what is 0K? You can comment your answers in the chat box, no, if you're I don't know if you're too shy, or any volunteers. If you're having issues with your audio system, no, you can comment your answers in the chat box, or post your questions, no, if you're having issues with your audio system. Okay, so again, what my question is, what is 0K or absolute zero? Again, this is a chemistry concept. Anyone? Yes? Any volunteers? No heat? Sige, when we say no heat, let's try to make more sense of this. Thank you. No, that's essentially the definition. No heat present. What is it in Celsius? Yon, okay, thank you. Somebody answered negative 273. So as long as you're not operating at 0K or negative 273, there are sources of heat around us. The tayo nasa Earth, the sun itself is the source of heat. That's why through of course, you guys are more inclined sa thermodynamics. That's why the heat distribution, with the heat distribution, various modes of heat transfer. We are living in, well, as for humans, livable operating or working temperature. So we have the room temperature. But there are sources of heat, no? Kasi we are not zero, we are not zero C, and we are, of course, definitely not zero K. And actually, zero K is um, very difficult to achieve. Actually, with the more recent uh, technologies developed by humans, we are still not able to achieve it, right? The closest thing we can achieve, as far as my most recent recollection, is something called the lambda point, nano Kelvin, no? 2.7, around 2.7 nano Kelvin. Lambda point, I think, is some point where condensation starts, no? Something called the Bose-Einstein condensates. Something related to quantum physics, those developments are produced, no? But 0K, still something that we have yet to achieve as humans. As far as I remember, no, if you maybe if you read something for more recent developments, can share, or you can let me know if someone has achieved it already. Achieving it is a tremendous challenge. Of course, definitely maintaining it is another challenge, no? If we can be able to achieve such a feat. So essentially, in general, in almost all cases, or in all cases that we know of, there will be sources of heat, no? Okay, so free electrons may exist by themselves, such as electrons moving from one plate to another, and then free electrons constitute the electric current in a conductor. Now, materials capable of having many electrons and which could carry electric current are called conductors. Yun. So, quick survey. Sige, so you guys have done 419. I think even in high school physics, these things have been mentioned before. So, what are the conductors that you know of? Any volunteers? Again, you can post your answers na lang in the chat box if you're having issues with your data connection or audio systems, no? Appreciate if anyone can share examples of conductors. Pag maraming free electrons, then these materials, or the materials are capable of having many free electrons. This can be, these are called conductors. In contrast, materials capable of having very few free electrons are called insulators. Can anyone share or recall any examples of conductors? Yan, conductors. Thank you. Copper wires, steel, gold, silver. Thank you for your inputs. Aluminum. Thank you, guys. So What can you notice in your examples that you provided? Very good. No? Thank you. No? So these are all metals. Okay. So next question. Materials capable of having very few free electrons are called insulators. So any examples that you can recall which can serve as decent or maybe good insulators of electricity? Any materials that you can think of? Yo. So I'm seeing examples already. Thank you. All right. Thank you, guys. No? So later we will see some more of these explanations. Okay. Thank you. Thank you. Yeah. So you've provided some of the good examples of insulators. Now, the thing is, somewhere in between, there are materials capable of having not so many free electrons. There is something in between. So it's called the semiconductors. Under some conditions, they are also capable of carrying electric current. There are some conditions. No? Now, the more free electrons there are in a material, the better it will conduct. So that's the key insight that you want to learn in this particular slide. So we'll go through the materials. No? So insulators possess no free charge carriers and thus are non-conductive. The atomic bond is based on shared electron pairs of non-metals. The elements which behave like non-metals have the desire to catch electrons. Thus, there are no free electrons which might serve as charge carriers. Electric charges do not flow freely in this material and that in an ideal in a sense that they can coat or provide a barrier between conductors to keep electric currents under control. No? So some of you have provided already good examples of electric insulators. No? So the most effective insulators are given here. Oil is another thing, no, that if you're not familiar with the use of oil as an insulator, these are commonly used by electrical engineers, no, to provide insulation sa mga malalaking motors, no, induction motors. How about water? No? Yeah, so there is a mention of water here. So what do you think of water as an insulator? It only works as an insulator if it's pure enough. No? Groundwater, because of the contaminants, the sediments, ions, no, it may not provide a good insulation. No? It can become a conductor because of the ions uh, floating around, no, sa water. Yon. Conductors, no? You've given the example of good conductors are materials that permit electrons to flow freely from particle to particle. Now, these allow for charge transfer through the free movement of electrons. And in any metal element, it contains less than 4 electrons in its outer shell or less than 4 valence electrons. Okay, so aluminum have 3 valence electrons. Magnesium has 2 valence electrons. Copper has 1 valence electron. Okay, so kaya pag in-arrange natin, these three metals. Copper is the best. No? Aluminum is a conductor but not so good. And somewhere in between you can have magnesium. No? So the best conductors are single element materials such as copper, silver, gold, and aluminum. Now, something in between, we've mentioned of the parang threshold or demarcation for valence electrons. We have the semiconductors whose conductivity lies between the conductors and the insulators, and that due to the exchange of electrons to achieve the noble gas configuration, semiconductors arrange as lattice structure. No? Lattice in a sense that they form crystals. You guys have your material science course, no? I cannot view. Okay, you're familiar with the concept of crystal lattice, no, in material science, right? Okay, so if these elements have four valence electrons, they can form crystal lattices, no, by sharing electrons with other silicon elements. Now, increasing temperature leads to broken bonds and free electrons are generated. The location at which the electron was placed, a so-called defect hole, remains. No? So that's how movement of electrons happen, no? By migration of electrons to the other. And essentially, the hole is filled by electrons from other elements. No? So, okay, so take a look at these set of examples muna, and then we'll go through the further description of the semiconductor materials. Okay, so yan. For the semiconductor materials, okay, so, right. And so the semiconductor materials can be classified as a single crystal, which has a repetitive crystal structure as germanium, no, silicon, single element semiconductors also are. And so I like you guys to ano, do you have your periodic elements ready? Okay, can you look at your uh, periodic table rather? Periodic table of elements. Do you have your periodic table of elements ready? Okay, so for those who are on their desktops or laptops, then you can check online for the periodic table of elements. So can you locate the semiconductor materials? Show of hands or reacts, no? If you can locate the semiconductor materials in the periodic table. So can you see the silicon or germanium? Show of hands and reacts if you can see the silicon or germanium. And then what other materials are there? What other materials are there? You can comment no in the chat box. What other materials are there in the same column or family of the same column or family of the semiconductors? No, it's mentioned here, no? Na silicon, germanium. But there's something in that family. You can spot it sa same family ni silicon. Can you check ano yung nasa same column with silicon and germanium? On what family does it belong? Any inputs for those who are looking at their periodic table? Okay. Sige. We will just go through the examples, no? Yan. Single element semiconductors are antimony, arsenic, astatine, boron, polonium, tellurium, silicon, and germanium. No? Now, beside the single element semiconductors, there are compound semiconductors as well. And these are constructed of two or more semiconductor materials of different atomic structure. No? So gallium and arsenic can form gallium arsenide, indium, and phosphorus is indium phosphide, gallium nitride, silicon carbide, what else? Silicon germanium. So these are some of the compound semiconductors. Now the three common semiconductors used are germanium, silicon, and gallium arsenide. But the most commonly used is silicon. Uh, and there's a reason for that, no? So if you think of the nature, what do you think is the most abundant source of silicon? Where can we find silicon in nature? Anyone, any idea where we can find silicon from nature? Or where is the most abundant source of silicon from nature? Okay, thank you guys. I'm seeing some answers right now. Any other inputs? Okay, thank you. No, so yeah, that's right. No, so it can be obtained from sand, right? That's right. But it requires a high energy process, no, to separate the silicon out of to come up with the pure silicon out of these materials. No? Because sand has something like an amorphous property. There are various elements combined, to form sand particles. So they're gonna have to heat up the sand and then perform a separation process. So have heat up and a molten sand actually. So that's very high temp. Okay? But essentially the raw material is free. It's just that it is an energy intensive process. No? Right. So the sand is formed into a crystal lattice as mentioned earlier, and it requires very high temperature to form crystal lattice. Yun, so to differentiate electrical properties of materials, we have to mention of the band gap. No? So band gap is the difference in energy between the valence band and the conduction band. No? So this is the amount of energy that the valence electron must have in order to jump from the valence band to the conduction band. No? So semiconductor requires some energy, for it to be able to conduct electricity. So that's why, as mentioned earlier, semiconductors can conduct electricity at some certain conditions, and that band gap is something that you have to overcome so that it will conduct electricity. Now, where is the source of energy? As I've mentioned, from the environment is possible. In the case of conductor, the valence band and the conduction band, they are overlapping. That's why with the ambient condition itself, conductor na siya. Nag-aalaw na siya ng flow of electrons or electricity itself. But with the semiconductors, it will require the material to heat up before conduction band takes place. Now, for the case of insulators, the band gap is very wide, no? That in so many cases, before you hit the conduction band, that the material may be damaged already. So let's say for some insulators like rubbers, it requires so much heat or so much high temp that tendency is that you have damaged already the material before you hit conduction band. So that's why in the analysis or design of wiring, that's critical, no? That the current ratings are being followed, no? Because if you do not follow the current ratings of the cables, wires and cables, the insulation material may not be thick enough or good enough, to support and maintain the insulation properties. So if you have a very small wire, tendency is that with the smaller wires, you heat up the cable and then it will provide sufficient energy so the insulation can melt down and then the material will be destroyed. So that's the case of for the insulators. You can the tendency is that you if you increase the conduction, the energy available in the environment, the common form is through heating. You damage the material before you reach conduction band. Now, we're mainly concerned about the semiconductors and that there are various ways to uh, control the flow of electricity or currents in conductors by heating this conduction band. So going back in the basic structure of the silicon and germanium, these are mainly described by four valence electrons in the outer shell. Now, that's why I was asking earlier, no? So can you go back to your periodic table of elements? And can you look into the table if there are any other materials having the four valence electron? Want to look into the same family, no? Okay, can you look? Can you check your periodic table? The elements, other materials besides silicon and germanium having the same four valence. Okay, no? Yes, that's right. Huh? Yeah, no. So, yeah, the thing about that element 114 is the properties are yet unknown, no? And in the case of SN and PB, there are various explanations why these materials are not semiconductors. Actually, lead is a conductor, no? Kaya yun yung pinang-solder natin, ang lead. So it makes more of a conductor than a semicon. But the first one, yan, carbon is a rather interesting one. No? Okay, so the thing with carbon is that, as we are saying, sa case ng example na lang, no, sa silicon, for us to be able to create semiconductor devices, we need to form crystal lattice out of these materials. So sa case na silicon, out of sand, we have to subject the sand or this material to very high temperature. So it will melt, and then some separation process will remove impurities and a crystal lattice, no? A single crystal lattice out of silicon can be made. So in semicon manufacturing, it's called the ingot, INGOT, no? An ingot out of crystal lattice. Now imagine what happens if we try to do the same for the carbon element. How do we make a crystal lattice out of carbon? Okay, so I'll just rephrase my question. What do you think will be formed if we attempt to make crystal lattice out of carbon? Yan. That's right, no? Somebody answered. Okay, somebody answered diamond, no? So it's a rather complex process, no, for us to create semiconductor devices out of diamond, no? Una, it's very costly. It requires very high amount of energy to form the crystal lattice itself. And of course, the processability is very difficult. And the energy levels then is very, very high. No? Later we will go through the different energy levels. But imagine if we can create diamond. There are various technologies. No? In Germany and Switzerland, I think they are able to produce synthetic diamonds. But those are very energy intensive processes. Some are saying that it exhibits, no, as a diamond as a material exhibits superior uh, temperature or thermal properties, no, because of that relative stability. Okay, but then again, the processability and the energy levels. Yeah. So uh, germanium, of these semiconductor materials, germanium has 32 orbiting electrons and has 4 valence electrons. So silicon is also a 4 tetravalent. Now gallium is a trivalent and arsenic is a pentavalent. But if we combine these two things, no, with the equal, parang sort of equal proportion, we can produce, yun, we can produce materials out of gallium and arsenic because the three vacancies with the trivalent you have one vacancy, with the pentavalent you have one excess, so it makes up for the missing pieces, no, for each electrons. So the effect is something similar to what the intended structure happens, no, in the case of silicon, where you have a 4 valence and 4 vacancies. These are completed by the nearby or adjacent atoms. So same thing happens with the germanium because of that uh, quadrivalent properties. Yeah, so for the current movement, the energy band for an atom in pure uh, silicon at its lowest energy state, there are no electrons in the conduction band, no, at 0 K. But at room temperature, sufficient heat allows for some valence electrons to jump the gap from valence to conduction and allows it to become free electrons. So free electrons are also called the conduction electrons. So again, as I mentioned, from room temperature lang, it provides sufficient heat already. Now, the exchange or the external heat provides sufficient energy to knock off the outermost electron. And so there are exchanges of energy, of electrons. The electrons knocked off from one atom in the lattice goes through the another one. Now, for every electron raised in the conduction band by external energy, there is one hole left in the valence band, creating something that is called the electron pair. Now, this uh, pair results to a recombination when conduction band electron loses energy and falls back into the hole in the valence band. So it can go through the other slots. Now, there are various movements possible with these. Okay, so intrinsic semiconductor is a material that has been refined to reduce the number of impurities to a very low level. Free electrons in a material due to external causes are referred to as intrinsic carriers. The number of intrinsic carriers vary from one material to another, and then electric current in a material is dependent on the number of intrinsic carriers and relative mobility of carriers. Relative mobility of free carriers in a material is the ability of free carriers to move throughout the material. So you can see na across different materials, we have varying numbers of intrinsic carriers, and the number of intrinsic carriers determines the mobility factors as well. Right, so the change in temperature of a semiconductor material can increase the number of free electrons quite substantially. Semiconductor materials such as germanium and silicon shows that the reduction in the resistance with the increase in temperature are said to have negative temperature coefficient. Okay, so as the temperature increases, the resistance uh, decreases. So it's the opposite. Conductors, on the other hand, have temperature positive temperature coefficient where an increase in temperature increases the resistance. Okay, so the explanation is that with the higher temperature, parang you have more free electrons that it gets flooded na the lattice. Right. Intrinsic semiconductors are or extrinsic semiconductors are semiconductors that have been subjected to the process called doping, no? Which is a process of adding impurities to pure semicon materials to alter the electrical properties. So there are two types, no? There is an N type and there is a P type. Now the elements for doping are either 5 or pentavalent or trivalent. No? So we have a pentavalent and trivalent. And you can see here that the trivalent or trivalent materials are used to create P-type doping, and pentavalent materials are used to create N-type doping. Yeah. So an example of a trivalent element is boron, indium, and aluminum. No? While a pentavalent uh, example is phosphorus, arsenic, and antimony. So gallium is also trivalent. So we have the parang mnemonic back then. No? Big paa. Boron, indium, gallium, and in some cases aluminum. For the trivalent, phosphorus, arsenic, and antimony for the pentavalent. Yeah. So there's a summary. You have the semicons in between. Pentavalent yung paa. And then trivalent is your big aluminum. Okay, so what happens after doping? Now, if you have a silicon lattice and then you introduce pentavalent, no? Pentavalent material. Like in this image, we have an antimony. No? So the fifth electron will not uh, fit into the lattice. So there will be an excess of fifth valence electron. Because it will still rearrange itself as a lattice, because of the intermolecular forces, and that the lattice is structurally sound, or a stable configuration that that the last lattice, the atoms itself will align and structure itself according to a lattice. Now, for the case of the antimony, the fifth electron will provide an excess valence electron because of its pentavalent nature. And so, with these excess electrons in a lattice, you have numerous antimony. Hindi lang siya isa. So with these excess electrons, the entire lattice will be formed into an N-type material. No? Well, not really negatively charged or negatively polarized, but just a notation or a nomenclature to describe the result of the excess ano, fifth valence electron. So in the case of N-type material, you have a majority carriers which are electrons. So we call this a carrier of electric current, no? Because you have excesses, you can use it to carry currents. And then the minority carriers are holes because of the external factors or heat. Of course, there will still be holes produced out of the thermal effects. On the opposite, if we introduce a trivalent material for the doping process, like the boron that we have here, similarly, it will rearrange itself into a crystal lattice because of the silicon majority. Doping is a introduction of very small number of other element. No? So the boron is minimum. And so you still have the majority as a silicon. So the crystal lattice itself will still follow the structural arrangement of the silicon. No? Yung mga ligaw na boron or any trivalent element will align itself into that lattice. However, a void or a vacancy will be provided by the boron because it is a trivalent thing. No? And so with the doping process, you have many boron atoms in that lattice. So the material itself becomes flooded with this vacancy called the holes. So that is why we call this as the majority carriers. So this will allow further flow of electricity in that material. We refer to this material as the p-type. No? Again, this is still neutral. This is not positively charged. This is not positively charged material. But because of the the majority of having vacancies as introduced by each boron atom, we have to come up with a nomenclature for that. No, so in that sense, we call that the uh, p-type material. Now, what is the effect of the Hall conduction? If the valence electron acquires sufficient kinetic energy to break its covalent bond to fill the void created by a hole, then a hole will be created in a covalent bond that releases the electron. There is therefore a transfer of holes to the right. So that's how the movement takes place. Hole current is the same as the conventional current. Are you guys familiar with that concept? The conventional current? Show of hands or any reacts if you're familiar with that concept of conventional current. Okay, so the thing is that um, earlier studies of electrical currents uh, assumed na current goes from positive to negative, no? But with the discoveries of the atomic model, with the discoveries of the elementary particles, it was later proven that it's not the positive charges are moving, no? But the electrons. It's actually the electrons are moving. But since the earlier textbooks were written with the assumption that there is a positive flow from positive to negative, the circuit analysis studies maintained it that way. That's why it's called the conventional current. In reality, if we go back to chemistry or physics, it is the electrons that are actually moving. So that is actually electron flow. We the earlier physicists us just maintained for the sake of consistency to use the conventional current as a means of uniformity, no? Because that was the previous assumption. Now, whole current flows only in p-type semiconductors. Likewise, electron flow is the current in n-type semiconductors in all wire conductors. The resulting p-type material is, again, as I mentioned, is electrically neutral for the same reasons as for the n-type material. A hole has the same amount of positive charges as a proton, equal to that of electron, but opposite in polarity. However, a whole charge, so this is worth noting, no, that the whole charge is not a proton. Okay, are we guys clear with that? Okay, and then a proton is stable charge in the nucleus that is not free to move. A hole is a positive charge outside the nucleus, present only in semiconductors because of unfilled covalent bonds. Whole charges can be moved by an applied potential difference. No? And that's the end of our presentation. So we're supposed to cover later yung semiconductor diodes, no? But it's rather more lengthy material. So we will try to start siguro next meeting siguro a faster pace, no, for the semiconductor diodes. And then this will be followed by uh, the discussion on transistors. Okay? Yeah. So any questions, concerns, or clarifications so far? If none, can I see a show of hands if everything is clear up to this point? Yeah, thank you. Okay, now so yeah, so I guess that's it now. So I will share the materials na lang later, and next week we will go through the diode discussion. Let's try to check if we can cover until the applications, no? So at least in a single day we can focus on the diodes alone. No? So again, guys, reminder for the survey, the link is posted last Feb 10. Let me check if yeah. So I reposted the link here. So kindly accomplish na lang the survey. Siguro I'll use the same survey na lang as your attendance for today. No? So please accomplish the survey, and again this will serve as your attendance for today. Okay, so any questions, concerns, or clarification so far? Okay, so thank you guys. No, if none, then I'll see you guys next week for the discussion on semiconductor diodes and devices.
Sir, excuse me po.
Yes.
Pag po nasagutan na yung forms na nakapost sa G Classroom, mag-fill out po ulit dun sa ipinost niyong link ngayon dito sa meeting.
No need na. That's actually the same form naman.
Thank you po.
I just like to emphasize na that you want everyone to accomplish the form or the survey. All right. So I guess that's it. And I'll see you guys next week and have a great week ahead.
Thank you po, sir.
Thank you po.
Thank you po.